Alright. Assalamualaikum. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and good day everyone. So today we're going to be looking at another topic in our lecture, which is greedy algorithm. So far, we have looked at the divide and conquer approach, okay, whereby whereby it is an approach where you can solve a problem by if let's say your problem have your problem can be divided into sub problems. You can actually divide and conquer it, okay, and solve and find the overall solution. And today we're going to be looking at another approach of designing an algorithm, which is called the greedy algorithm. Okay, so today we're going to be looking at the definition of what is greedy algorithm, as well as looking at one algorithm that applies the greedy approach, which is the Huffman encoding. Okay. All right. So recap. So as I mentioned, we whenever we want to design an algorithm, there are several approach that you can take in order for you to design that algorithm. Okay, and we have looked into the divide and conquer. Okay, whereby if let's say you have a you can divide your problem into sub problem. You can actually recursively try to solve the problem by breaking it into a sub problem, and then find and combining it back to get the complete solution. Okay, so we have looked into the divide and conquer. Today we're going to be looking at greedy algorithm, whereby like this an approach. It's a very simple approach whereby uh, in greedy approach, in order for you to solve the problem, all you have to do is just determine what is the next best step to take next, okay, at each point. So normally greedy algorithm and dynamic programming is like how do you call that, connected. Okay, so in a sense, if like let's say a problem, you have a problem, sometimes you can actually solve the problem either using greedy algorithm or dynamic programming. Okay, so in order for you to optimize, okay, the solution. But usually, right, for when you apply the greedy algorithm, normally you will not get the most optimal solution in the end. But then, particularly for optimization, but then sometimes you need to use the greedy algorithm because it is much more simpler algorithm to use. Okay, because if you want normally for optimization problem, um, um, dynamic programming will normally would be a better choice, okay, for you to get the most optimal solution. All right, so for greedy algorithm, as I mentioned just now, how greedy algorithm solve the problem is that it always makes the choice that looks best now. Okay, so at each point, we try to look at what is the next best choice. All right, that is to make a locally optimal choice, in the hope that this choice will lead into a globally optimal solution. Okay, so normally greedy algorithm will give you some sort of like the best estimation of what is the optimal global solution. But then normally if you usually it does not give you the most optimal solution. You probably need to you need to use the dynamic programming in order for you to get the best optimal solution. Okay, but then sometimes you may want to just use a simpler algorithm, which is the in order for you to solve the problem. Okay, and then you can apply the greedy algorithm. All right, so so how how do you know that you can apply the greedy algorithm to solve a particular optimization problem? Is that you will check for these two properties. Okay, one, if that property have a greedy choice property, so in a sense you are able to determine, you know, like at each point what is the next best solution. Okay, and then it has an optimal substructure. Okay, so it has some characteristic whereby uh, um, um, you can determine whether, you know, like at that point of time, the substructure that you have built is optimal. Okay, and then if, like, let's say you have this property, then you can apply the greedy algorithm. Okay, so elements of the greedy strategy. So these are these are the steps, okay, in order for you to apply the greedy strategy. So in step one, so you need to determine what are the optimal substructure, and then after that, you're going to develop a recursive solution. You need to show that whenever you make the greedy choice, you will only you will only have one sub problem. Okay, so in a sense when so basically what it means is that whenever you add the greedy choice, you will have one only one sub problem. It's like you're adding into the forest of decision that you have made. Okay, and then in step four, you need to prove that it is always safe to make the greedy choice. And normally, so in a sense, you know, like you're not going to change anything whenever you sort of like choose what is the next best choice. Okay, to add into your sub problem. And step three and four can occur in either order. So either you prove it to be safe first, and then you add into your sub problem, or the other way around. Okay, and then in step five, you develop a recursive algorithm that implement the greedy strategy, and finally you convert the algorithm, a recursive algorithm, to an iterative algorithm. Okay, so normally, you know, the reason why here is this is I don't know whether this one is compulsory, because yeah, so normally when you have a recursive algorithm, you need to use a lot of memory when you do the calls, instead of iterative algorithm where you do not need any additional pointers. Okay, when you apply the when you implement the algorithm. Okay. All right. So this before we look at the success story, so let's look at where greedy algorithm fails first. Okay. So this is this is actually a situation where we call 0-1 knapsack problem. We're going to be looking at into this problem again, I believe, when we do dynamic programming later. But then here, in 0-1 knapsack problem, greedy algorithm does not yield the optimal solution. Okay. All right. So for example, okay. So what does it mean by the 0-1 knapsack problem? So let's say, for example, um, uh, you have a knapsack, okay, or maybe we can assume that there is a thief that have a knapsack, okay, and the thief can only carry 50 kg, okay, in the knapsack. And then there are three items that can be stolen, I guess, right? So, um, so basically, these are the three items, and the thief need to make a choice, which is the most optimal solution for him to carry inside his knapsack that will give him the most profit. Okay. So for the 01 knapsack problem, we assume that the item cannot be broken. Okay. So therefore, these are some of the these are some of the possible solution. Okay. Either the thief choose first the biggest size, and then the next bigger size, and then these are the profit. Okay. Or if you choose to take item one, which gives more value per pound, okay, per kg, and then it choose either to add in 20 or 30, right? It will still will not give but even though you know that 10 gives you a pound for value per kg, it will still not give you the optimal solution. So basically this is the most profit that you can get if you use the greedy method for 01 knapsack problem. Okay. But then um um let's say for the fractional. Okay, so this one is an this is for the fractional knapsack problem, whereby we assume that the item can be broken down, so you can get a better optimal solution. Okay, whereby you take the most value per kg or per pound. Okay, and then you add the next best one, and finally you sort of like take 20 out of 30 of item 3. Okay, which give you these profits. And doing a fractional applying greedy in a fractional knapsack problem gives you a much better optimal solution. Okay. So yeah, so this is basically showing you how the greedy algorithm could fail. Okay, in giving you the most optimal solution, but at least by applying this approach, you can somehow approximate what are the globally optimal solution, right? Okay, so now we're going to be looking at the Huffman code, which applies the greedy algorithm approach. Huffman codes is used to compress data, and normally by applying this encoding, you can save up to 20 to 90%. Okay, of the space. Okay, depending on the characteristic of the data being compressed. So normally when we want to do the encoding, we always we consider the data to be sequence of character, and applying the Huffman greedy algorithm will allow you to build up an optimal way for representing each character as the binary string. Okay, so let's straight away look into the example. So let's say, for example, we have this 1,000 character data file that we wish to store. And let's say, for example, these are the characters. I should not do that, I guess. So these are the characters, and these are the frequency. Okay, so basically A contain 45,000, 13,000, 12,000. Okay, 16,000, 19,000, 5,000, respectively. Okay, so normally if we use if you want to encode using a fixed length code word, okay. So normally what we do is we say that A would be encode as 000, 001, 010, 011, and so on and so forth. Okay. So if like let's say we use a fixed length code word as such, you basically we can approximate that um, the file can be encoded in 300,000 bits. Okay. And then we can actually optimize the encoding by applying the Huffman code, and basically creates a variable length code word, okay, whereby it will only use up to uh 2 to 4,000 bits. Okay, which is much lesser than 300,000. So now we are going to try and see if how are we going to apply the Huffman code to do the encoding, to create the variable length code word. Okay, so here are the algorithm. Okay, I think it's better for us to look at an example. But then let's first look at the running time complex, the total running time of this algorithm. So later on, you're going to see that when you apply this um, um, when you apply this code, when you apply the Huffman encoding, it is actually will give you a tree. Okay, so and therefore the running time complexity will be order of n log n. All right. Okay, so let's try and look at this example. Okay, so I normally prefer to sort of like write it in the form of a table. So let me do this first. So F is 5, E is 9, C is 12, B is 13, D is 16, A is 45. So this is the frequency. Okay. All right. So how does how do you construct the Huffman tree? Is that first you find what is the smallest frequency, the smallest frequency, and then you're going to add them up. Okay. So if you look here, the smallest frequency would be 5 and 9. So therefore, we are going to construct our tree as F, which is 5, and E, which is 9. And then we're going to total up the 5 and 9 to create an internal node 14. Okay, so we're going to create a node, maybe we call it N1 of 14. Okay, and this one is done. So the next step is we're going to find the next two smallest value again. So from here we can see that we have so we're going to look at the rest of this and try to find the next two smallest value. So now basically we can see here which it is 12 and 13. So 12 and 13, we're going to create the same thing again. So we're going to have 12, 13, and we're going to add and create an internal node of value 25. So we call this N2. So this is N2, which is 25. Okay. And then we do the same thing again. We look at the rest of the value and try to find what is the next smallest, next to smallest frequency. So here we can see that it is actually D and internal node 14, right? So with that, create, we're going to add this node N1 with 16. We're going to total this up and we're going to create another internal node of value 30. So we say node N2 and 3, sorry, we of value 30. We do the same thing again. We look at this value and choose which is which two are the smallest. So we have 25 and 30, which is the smallest, and we're going to combine these two nodes together. All right. So these two are the internal nodes. So we have N2. This is N2. This is N3. Okay, so this is N1. So it will be easier for you to see. This is N1. This is N2. So this is N2. This is N3. Okay, so that you will be clearer to you what happened here. Okay, so since we choose that N1 and sorry, N2 and N3 is the next smallest thing, so we're going to combine this N2 and N3. We're going to take this value and we're going to total up. So now we're going to create N4 of value 55. So this is N4. And then we do the same thing again, which is find what is the next two smallest number. So we only have these two left, and we're gonna combine these two, which is this is N4 with 45, which is A. Okay, N4 and 45, and we're gonna total up and create the final node. Okay, so since we have taken all, so this is your Huffman tree. Okay, so this is your Huffman tree. Okay. All right. So how do you create the encoding from this Huffman tree? So it's pretty simple. All you have to do is just that you mark each of the branches. So normally, one of the way is that we mark all the branches going to the left with 0, and branches going to the right with 1. Okay, same goes for all the branches 0, 1, 0, 1, 0, 1, 0, 1. Okay, and then in order for you to create that variable length code word, let's say for example for A, so now we can see the variable code length for A. Okay, so the variable code length for A is 0, 0, 0. Okay, because from here going to A is only 0. And then for B would be, where is B? B is here. So in order for you to get to B would be 1, 0, 1. Okay. And then C, 1, 0, 0. For D would be 1, 1, 1. For E would be 1, 1, 0, 1. And for F would be 1100. Okay, so these are your variable length, code length. Okay, so if you see here, this is the code. Okay, that we get from this Huffman tree. Okay, so please bear in mind that there are multiple ways that your Huffman tree could look like. Okay, you may like have your tree encoded in a different way. Like let's say for example, maybe this is one, this is one, this is zero, or so on and so forth. Or maybe your tree instead of this one on this side, it could be on this side, and so on and so forth. So the variable code length uh, can be varied depending on how you construct your Huffman tree. Okay. All right. Okay. So that is for the Huffman tree. Okay, and I think for this topic, it's a very short topic. But basically, what we want to do is just to understand how you can actually apply the greedy approach. We are going to see other algorithm as well that applies greedy approach in the next lecture. The graph algorithm, which is the graph algorithm. Okay. Yeah. So basically, these are some extras algorithm that actually applied the greedy algorithm method. So this is a problem whereby you need to provide a solution to selecting activity. Okay, so if like let's say for example you have this activity I, okay, this activity I, and you want to schedule what are the most optimal set of activities that you can do out of all these activities. Okay, and this activity have a start time as well as the finish time. Okay, so if you are applying the greedy algorithm, what you're going to do is that first you are going to first you're gonna arrange the finish time in an increasing order. Okay, so here you can see that the finish time 4, 5, 6, 7, it's an increasing order. Okay, and then what you're going to do is that you're going to select uh, select what is the which activity can start this the soonest after one activity ends. Okay, so choose activity that that start as soon as one activity ends. Okay, so what it means is that, so let's say for example we start with activity 1. Okay, and then it stops at 4. Okay, so we say we're going to choose activity 1. Okay, and then the next since this one finished at 4, the next possible activity would be definitely not 2. 2 cannot because it starts at 3. It's past its deadline already. Sorry, it passed the time already. Same goes for 3 because it starts at 0, which is before time 4. Okay, so I forgot to mention that we assume that these are uh, uh, per unit. So if like, let's say, for example, you have a timeline, so this would be time 1, time 2, time 3, and so on and so forth. So therefore, if like, let's say, for example, activity 1 starts at 1 and it will end at time 4. So of course, for the next activity to start, it cannot overlap with activity 1. Okay, so therefore, the next activity needs to start after times 4. Okay, so therefore, we cannot have 2, we cannot have 3, and the next activity that we can possibly do is activity 4, right? So activity 4, which ends at time 7. Now we're going to try and look what are the next activity that can start right after time 7. Okay, not 5 because start at 3, not 6 because start at 5, not 7 because start at 6, and perhaps the next best one is activity 8. Right? So activity 8 ends at time 11. Again, we're going to see 9. We cannot start at 9 because start at 8. Not 10 because start at 2. And perhaps the next best one is 11. So A, 11. And then it ends at time 16. Okay. So we have 1, 4, 8, and 11. So basically, so therefore, these are the maximum. We can say that the maximum subset of activities that you can do by applying and you get this solution by applying the greedy approach, whereby you find what is the next soonest activity that you can start. Okay, so if you notice here, these are only just one solution. Okay, one subset of solution, and basically by applying the greedy approach, we can actually get 4 activities completed. Okay, you can also have a subset whereby you start with A3 and then the next one is A9 and A11, but then this subset only contain 3 activities, and then by applying the greedy approach, you can get 4 activities. Okay, which is A1, 4, 8, and 11. And you can also find another subset that will give you 4 subset as well. If you start with 2, 5, and then you start, and then since it ends at 5, you can start activity 4, ends at 7, and then you can start with 9, ends at 12, and activity 11, which ends at 16. Okay, so you can also get this, how do you call that, solution as well. But basically, by applying the greedy approach, you can actually find one optimal subset. Okay, for scheduling a set of activities for this example. All right. So by showing you this, it shows that there are various solutions that you can get. It's just that when you apply the greedy algorithm, we assume that it will give you one of the optimal solution or an approximate of a global optimal solution. Okay, so basically that is what it is trying to show here. Okay, so another example that might interest you, which is the traveling salesman problem. So if you have a read around about this problem, so there are still normally this is like a benchmark. It is used for optimization benchmark. Okay, for because you somehow the traveling salesman problem is a problem that occurs multiple time in like let's say for example when you want to do logistic delivery. Okay, because this problem is very common. It's a very common problem, and the optimization solution is still being researched. Okay, and one of the approach that is being used to solve this problem is by doing the greedy approach. And it's just that if you're applying the greedy approach, the running time complexity is very bad. Okay, it's almost exponential. All right, so it is an interesting thing for you to have a read. Okay, because you're going to see that um, you're going to see that greedy may be a way to solve this problem, but it may not give you the best running time complexity. Okay, all right. So I guess that's it for this topic. Now we're gonna go into graph algorithm in the next lecture. So if you have any question, you can um, um, type it in the reply below, and please tag my name as well since sometimes um, I'm not aware of comment if you did not tag my name. All right. So if you have any question, just post your question below the video. All right. So I guess that's it for our lecture for today. Thank you, everyone.